Good evening, Internet. Do-do-do-do-do-do-do. Hello, Internet. Welcome. Happy day. Happy evening. Welcome to Everyone Loves Math. Glad you're here. I'm glad you're here. Let's see. Updates. Wednesday update. Let's see. No updates for today. Feeling better about the microphone. I'm feeling better, although sometimes the microphone gets into focus, but I've got a solution. Y'all just got to give me a minute. I'm gonna by Monday, I'm finally gonna have my microphone figured out so I can look cool. Other thing, not an official sponsor, but shout out today, Trader Joe's Mongolian orange chicken. Again, not a sponsor, but I will take your money. Trader Joe's Mongolian orange chicken. This is how good, and don't worry, we're going to get to the math. This is how good Trader Joe's Mongolian orange chicken is. Today I knew I wanted it for dinner, so I bought it twice, so that when I have it for dinner now, I got my backups in the freezer, just in case I get that hankering for that Trader Joe's Mongolian orange chicken. Again, not a sponsor, but I will be a shill for any sponsor, especially if I believe in you, like Trader Joe's. Not a sponsor. Okay. Speaking of, well, not a sponsor. Hey, so I run this website called Everyone Loves Math. Right now, you're watching the live show, which we do Monday through Thursday at 9 o'clock. So we're more than a live show, and we're less than a we, because we're just me. So let's talk about the things we can do on Everyone Loves Math. So before this show, I spend the early evening doing private tutoring. And so if you are someone that is interested in getting some private tutoring, where we do things at your pace, take care of your problems, there's a link to my Calendly page, and you could book a session right now. I've got all of my tutoring availability for the next 60 days up there. And it's easy with a couple of clicks. You too could get some private tutoring. There's also some message boards, which honestly I'm not really pushing yet because we're still building. I'm still building the site. But I do have message boards, and for folks that want more frequent math help, right now I have a free level and a $5 level, and they basically go to the same place, except the $5 level gets you the VIP question and answer. I'm going to tell you, this website's still pretty small. You ask me a question, and you're probably going to see a response on that site, and then you'll see the problem done during the show that evening. I can pretty much guarantee you that. So that's a great way to get your question on the show. So you can go to everyonelovesmath.com to do that. All right. Let's see. Oh, the other business. So for today, I do problems. I do math problems. And what I would love to do is I would love to do math problems that you suggest. You, the Twitch audience. There's a bunch of ways to suggest them. So I just showed you my website. You can put it on the message board, put a question there. How about, I can point that way, right? That way. That's a phone number right there. Look at that. That phone number is the Everyone Loves Math hotline. It's also known as my Google Voice number. And you can leave a message, send a text, send a photo, send a video. You send me something on the Everyone Loves Math hotline, I'm going to solve that problem on the show that night. I can pretty much guarantee you that until this site really takes off and we have problems of a different kind, I'm here to do your problems. So where did this problem come from? So let's talk. When I set up for the show, if there are no questions from the chat, then I pull questions from the homework help section of Reddit. And so I think I have like 6 or 7 questions tonight from the homework section of Reddit. And I think they're relevant to a lot of Algebra 1, Algebra 2, pre-calculus students. And so we're going to work those out. At any time, if you put a question, now that the show's going, the easiest way to ask a question is just right here in the chat. But if you put a question in, I will see it and skip to it. All right. So all of that having been said, let's do some math. So this problem, where might you see this problem? So technically, an Algebra 1 student would be able to do this problem. But if your Algebra 1 teacher gave you this, they might be mean. Most of the time, people are going to see this in Algebra 2. I believe the student that asked about this on Reddit is a college algebra student. So they wanted to simplify, and the person that did this online did a lot of the problem right, but then wasn't sure about how to reduce. So cool, let's do it together. I don't think I've done one of these yet on this show. So happy to do it. Let's see. All right, let me move my mouse so I get some space. All right, here we go. So, and I wrote this in my own handwriting because on the website it was formatted like crazy, so I just rewrote it. All right, let's simplify this bad boy. So, before we start, the good thing to do is always talk about what do you observe. And so in this problem, here are some things you could say. First of all, this is, let's see, there's two words that I would want to hear. Fraction, division. Those are the two things that jump out to me, because those are the two things that I know everyone gets worried about, are fractions and divisions. And so here's what we got to think. When we divide fractions, going all the way back to elementary school, we know we have to multiply by the reciprocal. We flip the fraction and multiply. So even though this looks disgusting, we're going to do the exact same thing. So that's the deal with the division. The other piece with the fraction part is, I can tell by looking at this, these are a bunch of quadratics. So I bet you they factor, and then we're going to be able to cancel a ton of stuff. That's normally what happens in problems like these. All right, so first things first, let's just take care of this division sign. Nobody likes this symbol in high school or college. I don't like it. Just change it to multiplication. Ooh, gross. So I'm going to copy that first fraction, x squared plus x. Okay, and then instead of dividing by this monstrosity, we're going to multiply by the reciprocal. And the reciprocal is going to be to take that whole fraction and flip it. So x squared minus 7x should go on top, and x squared minus 9 on the denominator. And now with that last fraction, that also needs to get flipped because we're dividing by both of those things. So we're going to put x plus 3 in the numerator and x minus 7 in the denominator. So if you, like me, were worried about the division part of this problem, nothing left to worry about. We now only have multiplication. So if we really wanted to, we could just multiply straight across and be done, but that's never how this goes, because we need to see if anything simplifies. So what I'm going to do is I'm going to take this thing, and I need a little bit of space to work. So I'm going to take this thing and I'm going to move it down a little, because we have 1, 2, 3, 4, 5, 6 parts to this problem, right? There's 3 numerators and 3 denominators, and we need to try to factor all of them to break them down. So here's what I mean. Now, if you're in Algebra 1, you're probably just learning this now, but know that this stuff does not go away, baby. So when we factor, let's see, x times x is x squared, and this one particularly factors into x plus 4 times x minus 3. And we know that because 4 times negative 3 is negative 12, and 4 plus negative 3 is just that 1x. So we're good there. This denominator, 2x, that's already factored. It's a multiplication problem. It's already factored. Let's see, x squared minus 7x. So this is a quadratic, but you know it's missing something. It's missing the constant term. So we can't factor it like a normal quadratic. This is going to be one where we factor out the x. So this is a greatest common factor problem. X squared minus 7x both have x in common. All right, let's see. This x plus 3, I'm going to leave that. That doesn't break down anymore. So I'm just going to put it in parentheses because don't know, I feel better when it's in parentheses, man. It's being multiplied. All right, the 2x is good. X squared minus 9. This is a difference of two squares. X plus 3, x minus 3. And then the x minus 7, I'm just going to package that up too. All right, so again, if you watch me do this, you see this factoring happens pretty quickly. If you're someone that wants to work on the speed of which you factor, one, I'd love to have you for tutoring. The second, I am working on videos right now to teach factoring and some shortcuts and some long ways to do it so that we kind of, the video's coming. It's coming. Trust me. All right. Anywho, so we have factored all of the numerators and all of the denominators. And now the question is do we see anything that can cancel or reduce to make 1? And the answer is it's kind of all over the place, right? So what do I mean by that? I see a x minus 3. Y'all see that x minus 3 in the numerator? Well, there's an x minus 3 in the denominator too. So bye-bye. X minus 3 divided by x minus 3, that's just 1. And 1 is invisible in a fraction. All right, let's see here. X minus 7 in the numerator as a factor. X minus 7 in the denominator as a factor. Bye-bye. Those cancel to make 1. Those simplify to make 1. Let's see. What else do you see? What else do you see? Oh, look at this. This is 2 times x. And there's an x right there. Bye-bye. Y'all didn't know I had that beautiful singing voice. I hide it. All right. So we got to remember, though, that there's still a 2. So look at that. I canceled the x, but there's still a 2 hanging out. All right. And then, oh, how about this? I see a boop, boop, boop. X plus 3 in the denominator and an x plus 3 in the numerator. Those both simplify to make 1. So we just had like some crazy cancel party, man. Look at that. Things got crazy in here. But they got crazy in a really good way because all this stuff simplified. So now what in the world is even remaining in the numerator? Well, let's see. The x plus 4 right there, that's for sure still here. But I think everything else is canceled out. Whoa. All right, let's look in our denominator. So in our denominator, the only thing remaining is that 2. So if you do this problem right, you do that division, that whole disgusting problem simplifies to that. Look at that. And so if you go over those steps, let's just remind ourselves of these steps because there weren't too many, but they're really important steps. So when we saw this problem, we said, okay, fraction division, gross. We need to multiply by the reciprocal to do the fraction division. So we did. We multiplied by the reciprocal. Then we said instead of multiplying straight across, which we could do, instead we did what we knew we had to do, which was simplify. We factored each little numerator and each little denominator. We simplified if there was the same factor, top and bottom. Those simplified to 1. And then when the dust settled, the answer came out pretty easy. X plus 4, all divided by 2. Groovy. Rational functions. That's what these are called. If you are in Algebra 2 or pre-calculus, these are coming, baby. These are coming. All right. Speaking of rational functions, I saw this question, and this was a neat question for reasons that you might not see right away. So definitely wanted to take a second and talk about this. There was a question that said, identify the asymptotes for the graph, I guess I should have said for the graph, of y equals 3x over x squared plus 1. All right. So, and the person that asked about this was like, is there an asymptote at 0? And that was their question. They're like, what's going on at 0? So here's the thing. If you are doing this problem, then you are in the rational function chapter probably, and you know what rational functions tend to look like. They have these like crazy asymptotes and stuff. And one thing we can do is we could go to Desmos and like play around with different rational functions. But if you're asking this question, you've already done that. You've already played with some rational functions. So here's where we're at. Let's talk about vertical asymptotes for a second. All right, so vertical asymptotes, because there's a couple different kinds. Vertical asymptotes, horizontal asymptotes, and then slant asymptotes, which this does not have. So vertical asymptotes are, so these, what we need to do is we need to find where the denominator equals 0. So when we look at this, I don't want to make this like too complicated, but a rational function is a fraction. And fractions go bad when the denominator is 0, right? If you do 5 divided by 0 on your iPhone, smoke comes out of the top. It says error. Smoke doesn't come out of the top, but you can't. You cannot divide by 0. You end up with like an undefined answer. So something bad happens if the denominator is 0. So the question is, what happens if we set this denominator equal to 0? X squared plus 1 equals 0. Well, here's the thing. This is not a difference of two squares. We can't factor that. We could move the 1, and let's do that. Let's try to solve this with algebra. Although some of you might be able to look at this and know where we're going. So we could subtract 1 on both sides, and we'd get x squared equals negative 1. And then what happens when we try to square root both sides? We get plus or minus, right, the square root of negative 1. All right. Well, if you're in Algebra 1 or Algebra 2 and you put that square root of negative 1 in your iPhone, smoke comes out the top. The reason is that this is an imaginary number. So what we know about this equation is that this equation has no real solution. So even though this rational function has a denominator, the denominator actually never equals 0, no matter what we put in. And if we go back up, we can probably guess that by looking at it. Think about x squared plus 1. If you just put in 0 for x, right? 0 squared plus 1, that's 1. So we're good. We're not dividing by 0. If you put any positive number in, you're going to get a number bigger than 1, right? Put 3 in, you'll get 3 squared plus 1. If you put a negative number in, negative 3 squared, that's 9 plus 1. You're never going to find a number that makes the denominator 0. So let's see what this graph looks like. So we could totally go to Desmos and see what's up with this. So let's do that. All right. All right, so let's see. This function was it 3x? Oh my gosh, my memory is so bad. 3x over x squared plus 1. All right, so I'm going to type that into Desmos. 3x over x squared plus 1. And you get this really weird graph. Most rational functions do not look like this. This is kind of new. But if we look at this thing and we can zoom in, zoom out, do whatever you got to do, we don't see that same asymptote, vertical asymptote. There's nowhere where there's like a vertical place where this graph doesn't go. So this graph actually doesn't have any vertical asymptotes. If the denominator is never 0, then we're never dividing by 0, so it's all gravy. Any x value is cool. All right, so now let's talk about horizontal asymptotes. And one of the mistakes, because I like to go over this because I don't want y'all to make the same mistakes that other people make. So one of the mistakes that people make is they think that vertical asymptotes and horizontal asymptotes are like related to each other, and they're not. So vertical asymptotes are about where the denominator is 0. It's a very specific thing. Is the denominator ever 0? And if so, what happens at either side of that? For horizontal asymptotes, which we'll write in here. So horizontal asymptotes answer the question, what happens when x gets really big? We can say that x goes to infinity. Or when x goes to negative infinity. We could write it like that. So horizontal asymptotes are interested what's happening on the outside of this graph, far left and far right. That's what we're interested in. So there are a bunch of ways to think about this, but I'm just going to take this one problem as an example, and I'm going to make it not that deep, okay? because we can do this problem with mental math. All right, check this out. Let's pick a number far to the right, like a million, right? If we pick x as a million, then the numerator would be 3 million. That's a big number. All right, 3 million. But look at the denominator. The denominator would be a million squared plus 1. If you take a million and square it on your calculator, what is that? That's a 1 with 12 zeros? That's a huge number. So in this problem, what we can say is when x gets really, really big, and we can just answer this right here. When x is really, really big, y gets really, really close to 0. Because a fraction where the denominator is really huge, the denominator gets way bigger than the numerator, like 1 over a million, right? Or a million over a bazillion. That fraction is going to be really, really small. It's going to be close to 0. Now, what happens when x goes to negative infinity? What happens if we pick a really negative number way out there? Well, the numerator would be negative 3 million, right? If we pick like negative a million for x. And the denominator would be this huge positive number. So we would have a negative number up top, a huge positive number on the bottom. And so algebraically, we can say that algebraically, if x is super, super negative, y gets close to 0. Y would be negative, but it's getting close to 0. And if you look at the graph, let's go back to Desmos. Boop, 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 boop. That kind of proves out on our graph. Look at the outside far left and far right of our graph. If I pick this thing and start going to the right, look at this. This graph keeps getting closer and closer to 0. It's not going to negative, right? The y value is getting closer and closer and closer to 0. So close that if I go out to 50, it looks like or 60, it looks like it's right at 0. But we did this before. If you zoom in, you can see it's close, but it's not exactly 0. So, hey, I thought that problem was kind of fun. You know? Super fun. All right. Cool. So that's, those are the asymptotes there. So with this one, where the person got confused, I'll just tell you, is there's a horizontal asymptote at y equals 0, but there's no vertical asymptote. So that's where that person got confused. All right. I think I'm going to maybe skip this one for now. Boom. I'm just looking at the clock. Boom, boop. That problem took a minute because, you know, gnarly. All right, let's take a geometry break. I love geometry. So ABCD is a kite. So they're telling us it's a kite, which tells us a bunch of stuff. It says AB is 16 and AC is 12. Find the length of EB. So they want this length. Where are we going to do? EB right there. So they must be using X for that. I'd probably put the X right on top. And then the other thing I might do, let's just do it now, is if AC is 12 and this is a kite, I would probably rather label this 6 and 6 because that 12 kind of confuses me. You know what I'm saying? That's it. So this was just kind of, the picture was a little weird, and I think what the teacher wanted in this problem was to make sure that you read that picture really easy. So we've already assumed one property of kites, which is the diagonal AC is bisected, but that is a property of kites. The middle part of the kite cuts the kite in half. Now, let's see, the other property of kites. The diagonals intersect at a right angle. That is a property of kites. And so if we take advantage of those two things, then we realize, oh, look. And we end up here so much in geometry. Oh, look, it's a right triangle where we know two of the sides and we need to find the third side. You know what I mean? And this is like, man, this is close to tattoo status. You might get, if you're looking for a good math tattoo, you know what a good idea for a math tattoo is? Something like a squared plus b squared equals c squared. Why do I feel like I'm close to getting this Pythagorean theorem tattoo? I don't know. I'm not. I'm not wishing that into existence at all. But it'd be kind of cool. Okay. Anyway. All right. So what do we got? So the only issue with the not quadratic formula with the Pythagorean theorem is we have to make sure that we put the hypotenuse in for c squared. That's the only thing that we have to make sure we're good. And in this problem, the hypotenuse, the side that's across opposite of the right angle, is that 16. So that's pretty much all the information I need in order to do this. I'm going to write 6 squared plus x squared equals 16 squared. And now we're in a spot where we basically have a two-step equation, although it has a squared. So let's multiply this stuff out. We'll try to get x by itself, you know. So this will be 36 plus x squared equals 16 squared, which is 256. And now we're going to subtract 36 on both sides. And if we subtract 36 on both sides, we end up with x squared equals, oh, that's 220. And so now we have to take the square root of both sides. So we'll say take the square root of the left side, take the square root of the right side. Now normally, I'm just going to pause for a second. Normally, when we take a square root, we got to put the plus or minus. But I'm not going to do it here. And the reason is that we're looking for the length of a side. And so I know it's going to be positive. I don't have to worry about saying, oh, it's negative 2 inches long. No. Okay. So let's see, square root of 220. Ugh. Well, at least square root of x squared is easy. Now with 220, we got to see, can we take out any perfect squares? Does this thing simplify? So here's where, if you're in geometry, you got to ask your teacher, do you accept 220? Do they want a decimal answer? What does it say here? They want the exact answer. So the exact answer is the square root of 220. We can't put that in a calculator and get a decimal because that'll give us an approximate answer. All right, but then there's another question to ask your teacher. Once you know you want an exact answer, the question is should we simplify the answer? That's probably we do. So let's just do it. In order to simplify this square root, we are going to break up the square root of 220 into two pieces. We're going to break it up into what I like to call good stuff and what I like to call junk. All right, so I call it good stuff and junk. I put good and junk. Now, we're going to factor 220. We're going to rewrite 220 as a multiplication problem. But that's fine. We could do 2 times 110, but we need to do it in a smart way. So it's about time I define what good stuff is. So we're looking to square root. So in this problem, if we're looking to square root, good stuff are numbers that are square rootable. So for example, does 220 have a 49 in it? Then we could put that 49 up there because I know 49 is square rootable. Let's see. Well, 220 is even. So, I'm using my calculator because it's after 9 o'clock at night. So 220 is even. I can divide it by 4. Ooh, Joey. If I divide 220, first of all, it's red. Can't use red. Can't use red. That's how the devil enters. If we, let's see, divide 220 by 4, we get 4 times 55. So one way to break down 220 is 4 times 55. Why did I jump at that? Because 4 is a perfect square. So that allows us to actually take the square root of it. So the real answer to this problem for A students is you would simplify the square root of 4, and then the junk is there because it's junk. All right, I haven't even talked about this, but 55, it's not prime, it's 5 times 11, but that's the only way it breaks down. 55 does not have a perfect square in it, so we're doneskis. This problem is now done. Remember, x represented the length that we were trying to find, EB, and so the exact answer for EB would be 2 times the square root of 55. That's the exact and simplified answer. All right. I knew we'd need a little geometry break. And this is a problem that is similar, but also different. So I've just said stuff that doesn't make sense. Similar and different than a problem we did last night. So I just thought this was These are these problems where if you stop for just a second and think about it, you're going to have a much better time. So the person online just asked about 29, so I was going to take care of 29. If all 10 right triangles surrounding point O are congruent, what is the measure of angle BOC? So let's see. It wants the measure of angle BOC, which would be this angle. And it's talking about 10 right triangles. And yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 right triangles. Great. Okay. So what is that measure? Well, think about this. You know, a lot of times we think there's all these formulas to memorize, but a lot of times if you stop and do the common sense, it's not. So what do all 10 of those angles have to add up to make, right? So I'm going to step back here. We got the BOC, that's one angle, right? And then we got 9 more of them. If I trace out all nine more of those and get all 10 right triangles, what I just did is I just spun in a circle. And if you spin in a circle, then there's your answer. All 10 of those angles have to add up to 360 degrees. So if all 10 add up to 360 degrees, then one of them is just 1/10 of that, 36 degrees. Because if you have 10 36-degree angles, you have 360 degrees. You know, it's always good in geometry to like find a break where there's a formula you don't have to memorize and you can just kind of reason it out. That's always where you want to be. Because if you start memorizing, it's hard to stop. And then it fills your brain. All right. So, geometry break over. Sorry, hope you had fun with that. Break's over. Now we're going back to like algebra 2, pre-calculus. We're going to talk about logarithms. I think we got a couple of questions. I got a couple of questions to talk about logarithms. So, this problem was interesting because we haven't done one yet. We haven't done a logarithm problem yet. So they gave us this function. The function y equals a times the log base 5 of x plus k. It says it passes through these 2 points and then find the value of 3a plus k. So I wanted to do this problem for a couple reasons. Number one, it's good to review the logarithms. But the other reason why I wanted to do it is they asked to give the answer in this weird thing, 3a plus k. So like, what the heck is that? So if this is your teacher, what your teacher I think is trying to do is trying to ask a question kind of the same way that the SATs ask a question. So this whole thing about 3a plus k, that's going to be the easiest part of this answer when we're all the way done. First, we need to find a and k. And so look at this original function they give us. Let's just think about this for a second. I see a y, an a, an x, and a k. There are 4 variables right now, right? Because we don't know what a and k are yet. We need to figure those out. 4 variables is way too many variables to have in an equation. So when they give us a point, and this is true for any kind of function, if they say a function passes through some point, they're telling you if you put that point into the equation, you're going to get a true statement. So let's see what happens when we plug these points in to this function. So let me tell you what that looks like. We would say something like 4 equals the log based, oh wait a second. I need an a up there, right? 4 equals a times the log based 5 of 5 plus k. So what I did right there, and I know it's a little hard to see because this one's going to take up some space, is I put 4 in, I'll use my highlighter, put 4 in for y and 5 in for x. So that's what happened here. And I still don't know what a and k are, but at least now I've got an equation with fewer variables, only 2. Now, before we move on, the logarithm stuff, I'm not going to go into it tonight, but the thing that you should know is that logarithms are invented to be the inverse of exponents. They're backwards from exponents, so they cancel out with exponents whenever the bases match. So I know I said that really quick. We can spend some time going over logarithms. All you got to do is ask. But we do know enough to be able to evaluate this. The log-based 5 of 5 to the 1 is 1. So this is actually just a plus k. We could say a times 1, but I'm not gonna. All right, so one thing to know is that once we plug in that point, now you have to use some properties of logarithms to simplify. So again, logarithms undo exponents. So the log-based 5 of 5 to the 1 is just the exponent, that 1. All right, so then there was another point that they gave us. I'm going to do that alongside 25 comma 11. So I'm going to put 11 in for y, and we could say a times the log-based 5 of 25 plus k. So in this problem, I put 25 in for x and 11 in for y. All right. Now we have to evaluate this logarithm. So the log-based 5 of 25, well, 25 is, I'm just going to check this out. I'm going to rewrite 25 so that I can do this easy. Because 25 is 5 squared. So the log-based 5 of 5 squared is just the exponent, that 2. So this would be a times 2, so I'm going to write 2a plus k. All right. So I wanted to show this problem because, again, this problem involves a ton of work. It actually does. Why did I pick a problem to do all this work? So we have this log function. We've plugged in the 2 points. We've ended up with an algebra 1 problem because now we have 2 unknowns, a and k, and 2 equations. So if we have 2 unknowns and 2 equations, then we can use either substitution or the addition method in order to combine these equations to find the variables a and k. So here's what I'm going to do. Let's see. Why don't we just solve for k? Can we do that? So if I solve this first, because this first equation is easy, 4 equals a plus k. So can't we say that 4 take away a is k? For that, we just minus the a from both sides. So if that's the case, now we can combine these 2 equations and say 11, I'm going to start with that second equation, 11 equals 2a plus, and then instead of k, I'm going to write 4 minus a. That's substitution. See, this problem goes everywhere. And so now that we've found a smart way to combine those 2 equations, look what happened. Now we have 1 equation, 1 variable. I'm feeling the love. So what do we got? We got 11 equals 2a, take away 1a, right? Because that's really 1a. So 2a take away 1a is just an a plus 4. So what that means, let's see, what plus 4 is 11? A must equal 7. All right. Let's see. So we found a. Now let's find k. So to find k, we're going to use that equation we had. Remember when we said 4 minus a equals k? So a is 7. 4 take away 7 is k. And 4 take away 7 is negative 3. So in this problem, we found that k is negative 3 and a is 7. Now, this is where most problems would stop. Most teachers would say, all right, you're good. But then they asked, what's 3a plus k? So now we can figure that out. And here's where I want you to believe me, this is like the easiest part of the problem. Especially if I had a good memory and remembered, okay, a is 7 and k is negative 3. All right, so if a is 7, then this would be 3 times 7 plus negative 3. Right, you see how simple that last step is? Because I think that they're just trying to make it harder to figure out the answer. So what's this? 3 plus 7 is 21. So this would be 21 take away 3, which is 18. So after all that work, we end up with 18. Now, 18 has nothing to do with the graph. 18 is just where, they ask us for this random 3a plus k. So we did that at the end. All of the hard math had already been done at that point. You know what I'm talking? You know what I'm talking. All right, I'm going to take a quick pause. I'm going to check my hotline. All right, let's keep it going. All right, so we did a logarithm problem, and then I saw this, and this is a geometric sequence problem, and I'm like, oh, so exponents. You know, once we do logs, and everybody's excited, saying, hey, Joey, let's do exponents. So we do them. So in this problem, they ask, write an equation for the nth term of the geometric sequence, and then find a of a sub 6. All right, kind of pet peeve time. So I kind of think, so there's, everybody like talks about two kinds of sequences. This, you know, pretty much up until calculus, and it's arithmetic and geometric. Those are the two kinds of sequences. It's really messed up that they use A for geometric because that's confusing, but whatever, that's fine. Here's what you need to know about geometric sequence, because that's all, you know, that looks all complicated and official. Really what this is, geometric sequence, means there's a multiplication pattern. That's really where we see it. So, like you can see it right away in a question like 23. You see that as a multiplication pattern. How do you go from 2 to 8? Times 4. How do you go from 8 to 32? Times 4. How do you go from 32 to 128? Times 4. So, I'm not just really good at this. I know that geometric sequences are all about multiplication patterns. And so that tells me I don't have to hunt too hard to find the geometric sequence for any of these. It's going to be a multiplication pattern. So now let's talk about what the heck these are. So this is the formula for a geometric sequence. All geometric sequences can be written in this formula. And in this formula, you need to know a couple things. Let's see. A is the starting number. And R is called the common ratio. Now I'm going to give you some great news. It's Wednesday. It's time for great news. Here's the great news I'm going to give you. We already know both of these. Like, let's look at number 23. I'm just going to write 23 right here. We already know both of these. So 23, what's the starting number? The starting number is 2. So in this problem, A is 2. Remember how I said it's a multiply pattern? What do you multiply by each time? You multiply by 4. So the common ratio is 4. If we put this into the formula, we're done. So what I mean by that is we would say the formula for this, so we could call it AN or GN. We would say it's 2 times 4 to the n minus 1. That would be our formula. All right. And then finally, they want the 6th term of the sequence, right? It says A6. That's the 6th term of the sequence. So let's see. I'm going to just give us some space here. We're going to put 6 in for n, because n gives us the term of the sequence. So let's do it. 2 times 4 to the 6 minus 1. That's what we look like. All right. What would this be? 4 to the 5th power. I'm embarrassed to know I have that memorized. That is 1024. And so 2 times 1024 is 2048. So what that tells us is, I bet you, if we were to continue this pattern, right? Here's my highlighter. There's the first term, second term, third term, fourth term. If we were to multiply by 4 2 more times to find the 6th term, I bet you money that 6th term is going to be 2048. Boom, there we go. All right, so I'm going to cut today's stream just a little bit short because this is kind of a good stopping point. Today is Wednesday, so we're going to be back in the game tomorrow, Thursday, for our last live show of the week. There may be some gaming happening on this channel later on, but that'll be unrelated to the math. And in between here and there, if you have questions, if there are things that I can help with, then hit me up. Everyone Loves Math on Facebook, everyonelovesmath.com. You can email me at joey@everyonelovesmath. All right, y'all. that's it for me. Y'all have a great evening and stay classy out there.